So we'll go with the phase diagrams, but before that, we just want to reprise that we have discussed quasi-chemical approach, right, of modeling solutions. And in the quasi-chemical approach, what do? We basically assume the solution to be a large molecule which contains a lot of bonds, right, which contains a lot of bonds, which is basically the neighboring, the adjacent atoms forming bonds. So basically, it's like, if you think of this, it's a binary solution. It's a solution of containing two atomic species, two different atomic species. It's like A, B, A. It's random. So these are like you are forming in random. So basically, you have like A, and then again A. So it is going on in random. It's a very giant molecule. So, and this we are looking at this neighboring bonds. So we are looking at these bonds and we are trying to model it, right? So, and this is basically, you can do it on a lattice. So basically, if I think of this, if you think of this in a say, for example, for a solution, you can think of a lattice here, and we can think that, yeah, you have like different, these are like, lattice points, and you have like, this is an A atom, say, and this is a B atom, this is B atom, and then B atom, random, and putting some B, and then putting some B, depending on the fraction of B, and then I can put A's gap. So basically, it's a rigid lattice. If you look at a solution, then it's a rigid lattice. Even a liquid solution, we are always assuming the lattice to be rigid, right? Because now if you see, this is like a giant molecule and it's repeating, and in this giant molecule, what are the interactions that are possible? The interactions that are possible are, say, for example, it's AB interactions, and then there are AA interactions, and there are BB interactions, right? So if it's a binary solution, then it's this type of interactions are possible, right? Because cross, say, let us call cross as B and circle as A, then you have three different types of interactions that are possible. Now, if you look at multi-components, so for example, you have A, B, C, D type of components, then if you look at ideal solution model, then we assume that there is no interaction between the molecule, between the atoms, between the adjacent atoms, or we assume that the adjacent atoms interact in such a way that AB, say for example, the AB bond energy exactly balances the AABB bond energy, right? Because the half is there, because you have the two A's and here two B's, and here you have one AB. So basically, that's why you have to put half to avoid double counting. And if this exact balance is maintained, then what you get is like the AB interactions balances out AA and BB interactions. So that also basically pertains to ideal solution, right? Perfect solution. So that's why I told you last time that a perfect solution is where there is no interaction between atoms, but that means the interactions are zero. That means AB is 0, AA is 0, and BB is 0. But ideal solution is where you can have interactions, but the interactions balance out. Say AB balances out A and BB. Similarly, if it is like A, B, C, D, everything is working in pairs. So for BC is basically balanced out by BB and CC. So similarly, so basically, if you look at that, so in such a case, delta HM mix, that is the enthalpy of mixing, goes to 0. Molar enthalpy of mixing, molar volume of mixing is also 0. Only the configuration entropy of mixing remains, and which is basically given by minus R epsilon xi, which is basically positive, right? Minus R epsilon xi, where I can go from 1 to C, or I can go from A, B, C, D, E, and G. So instead of C, let us call it like I don't want to say number of components, say in C. Okay, so number of components. So basically, I go to 1 to n C, or I can be basically like 1, 2, 3, 4 up to n C, or I can be like A, B, C, D, whatever. So now, if that is so, and delta H mx is 0, since delta G equals to delta H minus T delta S, so we can write that delta G and mix, that is the molar free energy of mixing, equals to RT, right? There is a minus R. So minus TS. So minus TS means minus, and minus becomes plus. So this becomes RT, right? T is there. So RT xi and xi. So basically, as you can see, this is nothing but RT xi and xi. However, as you know, from the definition of activity, that there is all from the definition of activity or definition of non-ideality where there is interactions, you differ from it, and you have already discussed something called regular solution model, right, where we have looked at random Alloy approximation. Remember that we have looked at random Alloy approximation, and we told that in regular solution model the delta HM mix is not equal to 0 and is basically given by a regular solution order parameter omega. And see, I am writing it generalized, so basically we have done it for binary solution and we have written omega AB XB, right? Omega AB XB. So just make it slightly clean so that you can understand all the concepts. So see, if you look at that, so basically we wrote these, right? Omega ij xj. So we in a binary solution it is like omega AB say xb, where xi is the mole fraction of A and xb is the mole fraction of B, and omega AB is basically given by this 2EAB minus EA plus EBB, or you can also write this as EAB minus half of EA plus EBB, so whichever way you want to. And see, the idea here is that you have something called a coordination number, because you have, if you have, say for example, imagine one atom, if you think of square lattice, then it is connected by another atom here, another here, another here, and say another, right? So you have four. So if you just think of a square lattice, now in 3 dimensions, for example, in a BCC lattice or even in a body centered cubic unit cell, you have 8 neighbors, right? The coordination number is 8, right? Basically, one at each atom will have 8 neighbors. In FCC, like face centered cubic, you have 12 neighbors, they are equal to 12. For simple cubic, it is 6 neighbors, right? You have 6 neighbors, so you have one other neighbor like this, right? So you have along x, along y, along z, right? So basically along 1, 0, 0 directions, you basically have 6 neighbors for up to simple cubic lattice. So basically omega has the nearest neighbors, so nearest neighbor coordination number is there, so right, the z is there. So as you can see here, z is basically the coordination number, but the more importantly, the delta HM mix, that is the enthalpy of mixing, is not equal to 0, right? Not equal to 0, and you can write it, you can extend it to any number of elements, any number of species, right? Any number of different kinds of species. Say for example, A, B, C, these are like A, B, C, D, I can also write that. So A, B, C, D are, say, different atomic species, right? They are different kinds of atoms, right? If they are different kinds of atoms, then we can go on writing this omega xj. So basically this is nothing but sum I equal to A, B, C, dot, 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 and then j also equal to same. Only thing, j is not equal to I, right? So j is not equal to I, and you have omega j, and that is basically your enthalpy of mixing, right? So this is what is your enthalpy of mixing. And also we told, say for example, if you look at a binary solution or any one, you see omega ij is greater than 0, that means 2eij is greater than eia plus ejj, that means eij is less favored, that is the unlike bonds are less favored. So so you will basically see more of A and BB type of bonds. So we will have more of like bonds are coming together. So basically you have A clusters and B clusters, and that is called clustering, right? That is called clustering. So if omega ij is positive, there is a chance that you can see clustering. And when omega, right, because clustering means you have more AA bonds and more BB bonds than AB bonds. Now when omega ij is negative, then basically 2eij is less than eia plus ejj. That means eij is a favorable interaction, so because it has less energy, and so you will see more of A B type of bond. So basically if there is an A, then the adjacent in general, the adjacent atom will be having a different kind. It's like B. So if you have an A atom, then it is more likely for you to see a B atom as its neighbor rather than an A atom. So you will have some sort of ordering. But remember, although we are looking at clustering and ordering, we are still assuming this. So this is something very important. This is something that you have to realize. There is still this random error approximation. So basically, although you have clustering and you have ordering, and you are seeing, say for example, when omega ij is negative, right? When omega ij is negative, say here, then although you are seeing ordering, what you are seeing is you are more likely to see this guy bonding with this guy. So you will see more of these bonds and less of these, right? Less of like bonds. So you will see less of like bonds and you will see more of these bonds. So basically, if you look at that, I can put another cross here and I can still have, and I can put one cross here. So if you see, a circle is now basically neighbored by cross. So basically this is A and cross denotes B. Then you have more AB bonds than you have AA bonds, right? Similarly for B, you have more BA bonds rather than BB bonds, right? So you have more AB or BA bonds. That is the unlike, basically the unlike atoms or the atoms of different kind are pairing together, right? They are pairing together, and that is called ordering. However, why I am emphasizing on this is because although we are looking at this as an ordering where you have more unlike neighbors or more AB bonds or more IJ bonds, where I not equal to J. Okay, so that means more unlike bonds, but still that does not boil down to a ordered structure. It is not an ordered structure. It's not like atoms are occupying some specific lattice sites. It is not so. So basically what I am trying to say here is this. So if I look at one lattice, if I draw a lattice very quickly, say for example, I just try to draw one. So if I draw one, so if I have, if I want to draw another, so and then now think of this as say some excessive lattice. So if it is an excessive lattice, then what are the positions that are possible? So the positions that are possible are right. So there are also some positions like special positions like this. Face centers. Right? You have like 1, 2, 3. So each face will have 1, 5, and 6. So you have 1, 2, 3, 4, 5, 6. 6 face centers are there, and then you have also the corner positions. Right? You have these corner positions. Now, what I am trying to say is that when I am talking about a random error approximation, what I am trying to say is that you have an atom here, you also have an atom here, another here. Now, it looks like it's all one kind of atom. It is not so. It can be different kind of atom, but it is impossible for you to discern unless you go and look at it. And the probability of finding an A atom is basically the probability of finding an A atom is nothing but, as you remember in random error approximation, probability is nothing but the mole fraction of it. Similarly, probability of finding a B atom at a lattice site is nothing but the mole fraction of it, right? So and basically that means that you have an average. So this is like a disorder. So this lattice is called a disordered arrangement of atoms. Now in the disordered arrangement, you can have more AB bonds than AA or BB bonds. So basically, if I now look at that, if I give a tick, say for example, if I tell that I will highlight with a different color, say for example, this is a red atom. Okay, and red basically means say A, and say you have one this atom, and that we call say B. Okay, and so now you have one red atom here and maybe one here. So basically this is A and this is your B. So I'm just drawing a different color. So if you look at that, you have your A atom here, A atom here, maybe A atom here, and maybe another A atom here. So this is basically the front, right? The front face, and this is another A atom here. But then you also have the B atom. So basically, you have B atom. So this is your B atom. B, this is B. So something like that. So basically, you do not have any specific position. Like face centers occupied by A, and so as you can see here, that face centers or the corners are occupied by randomly by either A or B. So basically, lattice size. So if I tell this, the lattice size or lattice positions are randomly occupied by either A or, right? So that's the idea. So this is basically a disordered arrangement. In the disordered arrangement, you can have like omega AB. When it is less than 0, you can have more AB. Means basically what you are telling here is like NAB is greater than NAA or NBB in a binary solution, and in omega greater than 0, you are telling NAA comma NBB, that is number of BB and AA are greater than NAB, which is fine because this is called clustering. That's what you are calling as clustering, and this guy you are calling as, so this is basically order, right? So basically this is what you are calling as. So if I look at this, this is ordering and this is called clustering. Right? So this is clustering, this is ordering, but that does not mean that the arrangement has become ordered. When I talk about ordering, it does not mean, so in a regular solution model, you have to remember that does not mean that the solution has become ordered, right? Or, right? So you only have number of A and B bonds rather than AB bonds, right? This is something that you have to understand very clearly, because we will now distinguish between a disordered arrangement of atoms like in a regular solution model with the ordered arrangement of atoms, for example in ordered phase. So basically if you have a disordered phase which has a disordered, you have a phase which is basically, which has a crystal structure, the crystal structure of the phase is basically a disordered FCC or disordered BCC. You can model that phase using a regular solution model, right? You can use a regular solution model, a random approximation to model that phase, right? So if the phase has an underlying crystal structure which is face-centered cubic, but it is disordered face-centered cubic, then there is no problem. Some disordered arrangement, A and B are arranged in random, you can use a regular solution model. However, if A occupies specific positions and B occupies specific positions in the lattice, then you can no longer use a regular solution model. So Swalin in his book came up with one alternative model. Actually, if you look at CalFET has different models like sublattice models. These sublattice models can be applied to ordered structures as well as like ordered phases as well as disordered phases. That is phases with ordered crystalline arrangement and phases with disordered crystalline arrangement. However, please try to, so this is something that you have to understand, and this is very important to understand, that ordering or clustering in a regular solution model does not entail an ordered lattice, right? It is not an ordered lattice that we are looking at when we are talking of ordering. Ordering simply means number of unlike bonds like AB bonds is more than AA and BB bonds, right? Now we look at this ordered phases, right? So we are looking so far at disordered solutions or disordered solutions. This can be solid, it can be liquid, but these are disordered, right? Even if it's a solid solution, although it has a lattice and we are assuming lattice to be rigid and stuff, but we are telling that the arrangement of atoms in the lattice is completely random, because the probability of finding A is nothing but the mole fraction of A, and probability of finding B is nothing but the mole fraction of B. So basically, for disordered solutions, regular solution model which takes into account interactions is perfectly okay, right? From ideal solution, you have come to regular solution, because in regular solution you can now take into account the ordering and plus you can take into account the interactions. So basically, regular solution model. So please understand. So in regular solution model, why did you go to? Because you are describing interactions between different kinds of atoms, between the atomic species, between the components. So basically, the interactions give you a finite enthalpy of mixing, right? It is no longer zero enthalpy of mixing, like as in the ideal case. However, and it also leads to this clustering and ordering description, but still the idea is that regular solutions, you are always considering disordered solutions or disordered phases. You can call it disordered phases. So if you have disordered phases, now if I want to basically model ordered phases, that is phases with ordered lattice, okay, phases with ordered lattice. For example, you are looking at, say for example, this structure, you are looking at this structure. So if you look at that, this is a body centered cubic structure. However, I have given two different colors. One color, we are basically this red color that you can see here at the corners. Basically, we have also labeled it as beta. While the green color at the body center, we are labeling it as alpha. So as you can see, you have two different sides. One is called an alpha side, another is a beta side. Now you have these two special sides here, and beta sides are occupied by B atoms, for example, and alpha sides are occupied by A atoms. Then what you have is called an ordered arrangement of atoms or ordered lattice, right? You have an ordered lattice. You have sides that are very special, and the sides are occupied by either one atom or the other, right? It is not random anymore. So it's an ordered phase or ordered lattice. Now, in such a case, how do you apply a quasi-chemical approach, right? That is what we are going to discuss now based on the approach given by Swalin. Okay, in his book on thermodynamics, Swalin has given such an approach, and we are going to follow that approach, and we will try to see whether we can write free energy, the free energy of mixing in an ordered phase, right? So basically, if I can develop a free energy of mixing for an ordered phase, right? We have already developed it for disordered phases, right? In two ways. One is an ideal solution where we assume that there is no interaction or the interactions exactly balance out, and the regular solution where interactions can either be can lead to deviation from ideality, and the ideality can and the deviation positive or negative. In one case, you basically get clustering where you have more AA and BB or more like bonds than unlike bonds. In the other case, you have more unlike bonds than like bonds. But here you have already an ordered lattice, right? If you have an ordered lattice, the random alloy approximation does no longer hold, right? It does not hold. Random alloy approximation that you use for regular solutions no longer holds, and you have specific lattice sites. So you have unique. So you can tell that you have unique lattice sites. So these are unique sites, beta sites. These are the corner positions of the lattice, of the precise lattice, and alpha is the body centered position. Now, alpha is occupied by A and beta is occupied by B. And if you see this, and each corner is shared by 8 such unit cells. So basically, it's like 1 8, 1 8, 1 8, 1 8, 1 8, 1 8, 1 8, and 1 8. So 8 into 1 by 8 is 1. So basically, you have one alpha side and one beta side, and say alpha is occupied by A and beta is occupied by B. So you basically get a AB, right? AB. So you should means AB phase, right? The phase has a formula AB. An example, for example, is NiAl, and this structure basically is called B2 structure, which is a BCC derivative. It is derived from, so this is B2 crystal structure. It is a derivative. So basically BCC. So it's an ordered structure. It's a BCC derivative, right? So this is an ordered structure, order B2, which is basically derived from BCC, right? Where you have one beta site and one alpha site, and you get what is called a one B2. So this is called structure bit notation, okay, which is something that was used long back, and it has been used conventionally. So this is called a P2 line. But however, if you look at this, what has happened is, if you have a completely disordered structure, for example, you cannot distinguish between alpha and beta. If you think that you cannot distinguish between alpha and beta, what you have is a symmetry which is called FM3/m. So basically, if you look at the symmetry of this lattice, you get something called FM3/m. This is the space group of our FCC this structure is FM3/m, while here you cannot have F, you cannot use F, like in bias lattice you cannot use F, but this is basically P, because it's primitive, right? It's a primitive, because if you look at alpha, whether you are looking with respect to alpha or we are looking with respect to beta, you have a simple cubic structure or a primitive cubic structure. So you basically have a PM3/m symmetry. The symmetry is no longer FM3/m, but it has become PM3/m. Okay, so you can look at if you take a course on crystal structures, you will understand it better. But here, what you have to understand is very simple. You have to understand that this is an ordered phase where the site occupations are basically unique. So some sites like beta sites are occupied by B and alpha sites are occupied by A. It is also possible that some alpha sites are occupied by B. So in such case, what you have is like a wrong sites occupied by, or sites occupied by wrong atoms. So that is also possible, but the ordering changes, right? But so if you see, the transformation that we are referring to is called or disorder to order transformation. So this is called disorder to order, or you can do the other way also, order to order transformation. So this is what we are looking at. Now if you are looking at here, so what does that mean? So if I look at order to disorder transformation, spelling correctly, transformation, or you can also call it phase transition, but let us call it disorder to order transformation, right? So you have B1 structure. B1 structure is nothing but disordered BCC, right? This is same as disordered BCC, right? So disordered BCC means it has both A and B, but it is randomly. So it can be A, this can be B, this can be A, again this can be A. Again, I have to draw many unit cells, right? Because these unit cells, they are periodic in nature, right? They are basically infinite, right? In extent, these crystals are infinite in extent. It's completely bulk. There is no surface, and you have translational periodicity, right? You cover the entire space with these unit cells, and you have this so you have lattice, which is a BCC lattice, and you have motif these are motifs are nothing but A and B atoms. We are assuming that it is spherical, and you have say this is also B, and this is A, and this is B, and say this is A. Now you see, it's more or less a random arrangement. Obviously, for a random arrangement, for a true random arrangement, I have to take many such unit cells, right? And you have to describe many such motifs, and you have to. So if you put them all together, you will see that it is definitely completely random arrangement, right? It's a disordered structure. Now there is a temperature, so this is called a phase transition temperature or a critical temperature, below which this disordered structure basically below this disordered structure undergoes ordering, right? Ordering transformation, okay, or ordering transition. In such a case, that what happens, BCC converts to B2, And in P2 what happens? You have an alpha site which is occupied by A and beta site is occupied by B. Basically, you have now preferences means preferential occupation of A and B in unique lattice sites, right? Unique lattice positions, right? There is a preference in the occupation of A and B. Say, for example, A wants to occupy the green side and B wants to occupy the red side, right? So that is what is. So this is basically from a random arrangement. So this is called a random arrangement. So you have a random arrangement here. So it is like random, 2 and ordered lattice. So it's a random lattice, means random or disordered crystal structure. Right? It's a random occupation basically. Right? It's random occupancy of B and A. Here you have preferential occupation of B and A at special lattice positions. Right? So you have site preferences or site fractions. So a new term that will be introduced in ordered structures is basically site preferences or site occupation or site fraction. Right? We call it site fraction. Here we had only mole fraction. In a disordered lattice, we only considered mole fraction of A, mole fraction of B. We did not talk about site fraction. But here we will look at alpha site fraction and beta site fraction. Right? So basically, we will tell how many A atoms are in the alpha site, how many B atoms are in the beta site, and we will look at these sites, right, as special sites, right, as special positions in the lattice. So basically, even for FCC, right, even for FCC, we have such structures. Say, for example, you have gamma. Gamma is, say, for example, nickel aluminum. If you look at superalloys, there is a structure. This gamma structure is nothing but FCC, right? It's FCC, disordered FCC. There is random arrangement of nickel aluminum of A and B. So basically, if it is, so that basically random arrangement of different kinds of atoms. Right? So for example, it is nickel and aluminium. So if you have nickel and aluminium randomly occupy the lattice positions, right? Nickel and aluminium randomly occupy all the lattice positions. So that is a face center position or it's a corner position, it just randomly occupies the lattice positions. On the other hand, if you have an FCC derivative which is L12, again structure break notation L12. So common notation used, okay, for historic reasons. So L12, if you look at it, then you have nickel atoms. Say for example, nickels. These green atoms are basically say nickel atoms, and these nickel atoms are basically occupying the face-centered positions. Now each face-centered position is basically shared by 2 lattices. So basically half. So there are 6 nickel atoms, and half, and each is like shared with another lattice. So basically you have 3 nickel atoms, effectively 3 nickel atoms per cell, and you have 1 aluminium. So what you basically get is an ordered structure which is called Ni3Al or gamma prime. Right? It's called gamma prime. You can basically extend it to multiple components where you have specific components of specific species basically occupying their own preferential sites. These preferential sites can be, say, for example, titanium will occupy certain lattice sites, aluminum will occupy certain lattice sites, and so on, right? So this is something that gives you something called a gamma prime, which is an ordered arrangement, right, where sites are unique, right? Sites are now unique, and you have each site is unique, and you have this site, for example, occupied by nickel. All the face center sites occupied by nickel, while the corner sites are occupied by aluminum. Aluminum generally will not like to come here, but it does happen. It does definitely happen. So you have some change in order. Okay, so you have some change in order, and that is where we have to introduce something called order parameter, where we have and to introduce order parameter, what we first introduce is called site. The first thing that we introduce is called site fraction, right? So because the sites are unique, right? So site fraction, right? You are looking at the fraction of alpha sites occupied by A atoms and fraction of beta sites occupied by B atoms. Now, to do this derivation here, to do the derivation of this model here, we are assuming a B2 order structure. So, we are assuming a B2 structure, B2 order structure or B2 phase. So, or we can tell that it's a B2 phase. B2 phase has two types of sites, right? Alpha sites and beta sites. And if you see, the ratio of alpha is to beta is 1:1, right? You have 50% of alpha, you have 50% of beta sites, right? So, alpha site basically, for example, denotes the body centered position, and the beta sites are the corner positions, right? These two unit positions. If you again look at do a class on crystal structures, you will understand what I am talking about. These special sites. So, for example, the corner sites are special, and these are occupied by one kind of atom, and the body centered sites are special site, and that is occupied by other kind of atom, right? Now, if you think of that, now I am looking at fraction of alpha sites or site fraction. So, alpha site fraction. So, if I look at alpha sites, so fraction of alpha sites is nothing but alpha site fraction, right? So, basically we are looking at now, so we are telling alpha site fraction. But we have also, so basically now you see, how will I do the site fraction? Site fraction ultimately of A, say of one kind of atom, of one kind of or one kind of atomic species, right? You can call it A is the atomic species. So, one kind of now, if I look at that, so what we are telling here is that let R alpha denote the fraction of alpha sites occupied by right atoms. Right atoms, let us call these right atoms as A. So, R alpha is the number of alpha, is a fraction of alpha sites, not number, fraction of alpha sites occupied by A. Right? R alpha is the R alpha basically, if I write in other words, so R alpha fraction of alpha sites or A sites occupied by A atoms. Similarly, you can write R beta fraction of beta sites. So, right atoms means say for example A atom. So, R alpha is a fraction of alpha sites occupied by A atoms, and R beta is a fraction of beta sites occupied by B atoms. Now, if you quickly look at this, the fraction of alpha sites occupied by wrong atoms is 1 minus R alpha, right? So, that is basically denoted by W alpha or 1 minus R alpha. So, alpha sites occupied by fraction of alpha sites occupied by wrong atoms or B atoms is 1 minus R alpha. Similarly, fraction of beta sites occupied by wrong atoms or A atoms is 1 minus R beta. So, basically, so this is very, very important. So, basically, W alpha is the alpha sites occupied by B atoms. W beta is a fraction of beta sites occupied by A atoms, right? Beta sites occupied by A atoms. Now, if you see, if beta sites are occupied by A atoms and alpha sites are occupied by B atoms, you are slowly moving towards disorder, right? The more and more alpha sites are occupied by B atoms or wrong atoms and beta sites are occupied by wrong atoms, so slowly at one point of time you can go to disorder. However, if you have complete order, alpha sites will be only occupied by A atoms, that is the fraction of alpha sites occupied by A atoms will be exactly equal to 1. Similarly, so if alpha sites are all occupied by A atoms in a binary alloy, then the beta sites have to be occupied by B atoms. So the fraction of beta sites occupied by B atoms will be exactly equal to 1. So basically, R alpha equals to R beta equal to 1 corresponds to complete, right? We have written that. So we have written that it corresponds to complete order. So complete order is given by alpha sites exactly occupied by A atoms, that's the right kind of atoms, and the fraction of alpha sites being equal to 1. right? So R fraction of alpha sites occupied by A is exactly equal to 1, and fraction of beta sites occupied by B, that is the right type of atoms, is exactly equal to 1. So this gives you complete, right? This gives you complete. Now if you see, now if I look at probability, say probability or random alloy type of thing. So basically if we look at that probability of an A site or alpha site occupied by A atom, if it is XA, now you see, if it is on the other extreme, if the probability of an alpha site occupied by A atom is XA, that is the mole fraction of A or composition of A, right, in terms of mole fraction, composition of A in terms of mole fraction, then basically you have nothing but a complete disorder, because now alpha sites are occupied by A atom. That means alpha sites occupied by A atom, the fraction is the fraction of alpha sites occupied by A atoms is given by the mole fraction of A. If that is so, you are going towards the random alloy approximation. If that is so, when R alpha equal to XA, you get a complete disorder. R alpha equal to XA gives you complete disorder. Similarly, R beta equal to XB, complete disorder. Right? R beta equal to XB or R alpha equal to XA, what you get is called complete disorder. So what are the conditions of complete disorder? Either this condition or this condition, like R alpha equal to XA or R beta equal to XA. Therefore, if that is so, R alpha equal to 1, complete order, R alpha equal to XA, complete disorder, right? R alpha equal to 1, so if you look at that, R alpha equal to 1, order means perfect order or complete order, and R alpha equal to XA, complete disorder. Now we can define something called a long range order parameter in terms of R alpha and XA. How? Long range order parameter, we can define it in many ways, but this is one definition. L equals to that is given by Stalin, so it is basically L equal to R alpha minus XA by 1 minus XA. So R alpha minus XA by 1 minus XA, or R beta minus XB by 1 minus XB. Both are equivalent, right? So R alpha minus XA 1 minus XA is the same as R beta minus XB by 1 minus XB. Now when R alpha equal to XA, if you put it R alpha equal to XA, so then XA minus XA goes to 0, so L becomes 0. So L becomes 0, which basically denotes complete disorder. Now if R beta basically again equal to XB, say R beta instead of that I put XB instead of R beta I put XB. So then this becomes XB minus XB, which is equal to 0, and 0 by 1 minus XB is 0. So basically again complete disorder. However, if R alpha equal to XA, so if R alpha equal to 1 instead of XA or XB, say if R alpha equal to 1, so put R alpha equal to 1. So if it is that, so then this is 1 minus XA by 1 minus XA, so which is equal to 1. So L becomes 1. So if R alpha is exactly equal to 1, right? R alpha equal to 1 means complete order. R beta equal to 1 means complete order. So if I put R beta equal to 1, so 1 minus XB by 1 minus XB, L equal to 1. So complete disorder is given by L equal to 0, where R alpha is equal to XA, and complete order is given by R alpha equal to 1, or which gives you L equal to 1. Now in such a case, for this range, so L can be between 0 and 1, right? It can be equal to 0, which gives perfect disorder or complete disorder. Equal to 1, the equality tells complete order. So basically for this range from 0 to 1, fraction of A on alpha site or A site will be equal to alpha, correct? In general, from 0 to alpha 1, the fraction of A site can be is always denoted by R alpha, right? And let us consider total number of sites to be n. Total number of sites to be n. These are like the lattice sites, right? In these lattice sites, if you consider B2 structure, you have alpha is to beta. If you see alpha is to beta, these are like sites. Alpha site is to beta site, or you can also call it A site is to B site, because alpha site is basically occupied by A, say, and this is B site, the same, right? equivalent, which is equal to say 1:1. If it is 1:1, that is 50-50. Then basically, if your total number of sites, which is n, total number of sites is n, then you have how many alpha sites? You have 50%. So basically n by 2 alpha sites. Similarly, you have n by 2 beta sites, right? So number of A atoms in the alpha site is n by 2 into R alpha, because R alpha is basically the fraction of alpha sites occupied by A. So number of A atoms in alpha site is n by 2 R alpha. Similarly, number of B atoms in beta site is n by 2 R beta, right? This is n by 2 R beta. And now if you consider an alloy composition 50A, 50B or 50 atomic percent, so basically what I am talking about is like 50 atomic percent A and 50. So this is basically given in atomic percent. So atomic percent can be converted to mole fraction. So which implies XA equals to XB equals to half. Okay, now we are considering such an alloy, and we are considering that this alloy is undergoing disorder to order transformation, right? At this composition, it is undergoing disorder to order transformation below a critical temperature. Below a critical temperature, it is basically becoming ordered, right? Now, in such case, now if you see in such a case, L, which is R alpha minus X alpha by XA by 1 minus, so R alpha minus XA, XA is the mole fraction of A or composition of A, and by 1 minus XA. Now XA is basically put XA equal to half in the definition of A. If you do that, you have R alpha minus half by 1 minus half, which is basically, right, you have R alpha minus half by 1 minus half, which basically comes down to 2R alpha minus 1. Now 2R alpha minus 1 is equal to L, right? So if you put XA equal to half in the definition of L, you get L equals to 2R alpha minus 1, or R alpha, that is a fraction of alpha sites occupied by A, is 1 plus L by 2. R beta similarly, again you can do the same, XB equal to, so basically put XB equal to half in what equation? L equals to R beta minus XB by 1 minus XB. If you do that, you have XB equals to half, so R beta minus half, you have R beta minus half by 1 minus half. So basically you have the same result, only R alpha will be substituted by R beta, right? So R beta becomes then 1 plus L by 2. So R alpha in this case is 1 plus L by 2, R beta is also 1 plus L, right? Now if you look at the number of A atoms on alpha site, you have n by 2 R alpha, right? We already determined this, but you can now put R alpha equals to 1 plus L by 2. So this becomes 1 plus L by 2 times n by 2 R alpha, which is basically 1 plus L by 4 into L, right? Varying the total number of sites. Similarly, number of B atoms on beta side, so n by 2 R beta, which is again 1 plus L by 4 into L, right? So now fraction of B atoms on alpha side basically will be W alpha, which is 1 minus R alpha, and so B atoms on alpha side, so 1 minus R alpha into, so basically the number of B atoms will be 1 minus R alpha into n by 2. Right, so 1 minus R alpha is nothing but 1 plus L by 2. So this becomes 1 minus 1 plus L by 2, which is 1 minus L by 4, because there is a 2 here, there is a 2 here, and this becomes 2 minus 1 minus L. So basically 1 minus L by 4. Right, this is what we have. Now once we have done that, we get B atoms on alpha site as 1 minus L by 4 into n. Similarly, A atoms on beta site will be 1 minus L by 4 into n, but A atoms on alpha site is 1 plus L by 4 into n, and B atoms on beta site is 1 plus L by 4 into n. So basically, for correct sites, you have 1 plus L by 4 into n, where n is the total number of sites. So 1 plus L by 4 into n is the number of alpha sites occupied by A, or number of A atoms. Number of A atoms occupying alpha site. Number of A atoms occupying alpha site will be equal to 1 plus L by 4 into n. And number of B atoms occupying beta site, number of B atoms occupying beta site will be 1 plus L by 4 into n. But now, if you look at the wrong atoms, that is B atoms on alpha side, which is 1 minus L by 4 into N. Right? So basically, if you know this relation, say I will just write it clearly here. So if we write this way, number of A atoms on alpha sublattice or alpha side, by the way, this is also called alpha sublattice, equals to 1 plus L by 4 into. Similarly, number of A atoms on beta sublattice or beta side is called 1 minus L. Similarly, number of B atoms on beta side or beta sublattice will be again equal to 1 plus L by 4 into A. Right? Again, now if you look at number of B atoms on the wrong side or on alpha side will be equal to 1 minus L by 4. Now you are going to evaluate. Now you can evaluate the number of AA bonds with this information, number of BB bonds with this information, and number of AB bonds. How do you do that? See, probability of A and alpha is basically given by the fraction, right, which is R alpha, right? Probability of A and alpha, and probability of A and beta is 1 minus R beta, right? Probability of A on beta is basically 1 minus R beta, because R beta is probability of B on beta, right? So this is 1 minus R beta, this is 1 minus R beta, which is basically W beta. Now let us assume Z to be the coordination number of sides. Again, it's a BCC derivative, right? So basically the Z basically remains as 8, right? So each alpha side, so as you can see, each alpha side, like the body center, is surrounded by Z beta sides. Now you can see that if you look at the diagram, you will see that each alpha side, that is the body center, is basically occupied by 8 beta sides. Similarly, each beta side is occupied by 8 alpha sides, right? So basically, as you can see, Z is equal to 8, which is same as BCC, because it's a B2 is nothing but a BCC derivative. Now see, if that is so you have A on alpha and A on beta. So you can now look at AA bond. So basically, which is basically R alpha into 1 minus R beta. Now you have R alpha into 1 minus R beta into Z, right? That is basically probability of an AA bond, right? Between two sublattices, right? Alpha and beta. So basically, probability of AA pair is